Hello, profs and TAs of Software 437 Software Performance Analysis. Today we will be discussing the Sisyphus database retrieval performance anti-pattern. Once again, we are Group 14, Xander Sirwa, Jake Egan, Quentin Roy Foster, and Matthew Thompson. So, what is the Sisyphus database retrieval anti-pattern? So to begin, anti-patterns are commonly used solutions which generate negative performance consequences. So what this means is that while it's solving one problem, it just ends up creating more. So the Sisyphus database retrieval anti-pattern is named based off of the Greek legend of Sisyphus, where he's damned for eternity to push a rock up a hill just to watch it roll back down again and have to do the exact same task over again. So in reference to software performance, this is usually referenced in terms of when large lists are required or subsets of those lists, more specifically. So scalability issues occur with large frequently accessed lists because of the inefficiency of the subset extraction. So what happens is the web server requests the entire list from the database and then filters through that to extract the subset. So the central flaw with this approach is that the processing necessary to retrieve the entire list from which a subset is extracted has to be repeated for every single subset, rather than just requesting the subset from the database, which would lower processing requirements significantly.
The ramp is a scalability problem which occurs when processing time increases as the system scales. For example, if the response time for a user request increases over time, this phenomenon is known as the ramp anti-pattern. The Sisyphus database retrieval anti-pattern is a special case of the ramp. This anti-pattern occurs when performing repeated list subset extraction on a large list with an inefficient search algorithm. A common approach to list subset extraction is to search an entire list to find a subset. Each time a subset is requested, the entire list is searched again. This results in a longer response time if the list is large. Making repeated queries to a large database while only retrieving a small subset of the data is a common design in many software systems. So this is an important problem to use software performance engineering to mitigate. The anti-pattern is often not detected during testing because it is a scalability problem. If the tests are working with a small list of data, the problem will not be present. In practice, data will often be larger than the test data, so the anti-pattern will be detected only after the system is implemented.
One solution to the Sisyphus database retrieval performance anti-pattern is caching. So caching reduces the cost of full list retrieval on a per request basis by basically caching that first request, or at least the response to the first request, and basically using this cache as a source of data rather than querying the database every time a request is received. So data resides outside of the database after the first query, as I just mentioned, and some advantages of this solution is that resources are eliminated after the first access, and you only need to compute the total list size one time as it's cached after this first access. Some disadvantages to this solution, there could be some significant response time required for that first access because it's going to be a large request. It's difficult to maintain the cache state as requests come in, and furthermore, speaking to this, the consistency of the cache is difficult to maintain as multiple requests come in and as the system scales.
Another possible solution is the upper-lower bound solution. This method is an optimized version of the index-row solution. The index-row solution will not be covered in this presentation since it is simply a more basic version of the next two solutions. Upper-lower bound eliminates the dependency on the subset list start position. As the user moves through the subset from the start to the end of the list, The attribute values from the start and end of the subset provide additional restrictions on what is returned from the query. A simple version of the algorithm is seen below. End subset last name is the last name of the currently displayed item, and subset size is the number of items displayed in the subset. This algorithm reduces resources significantly. For example, database server, LAN, and web server are all conserved, and this is by restricting processing to only the list subset. Another possible solution is the sequence number solution. Sequence numbers build on the upper-lower bound solution by eliminating the need for unique attribute values. The sorting order is not needed since each element in the list is assigned a unique sequence number. The upper and lower bounds on the sequence numbers are used to return specific subsets. Indexing of the sequence numbers improves the subset retrieval and avoids sorting of the subset. The algorithm can be seen below. The variable lnamesec is a sequence number for the list sorted by last name and seen in variable lname. Performance gains for the sequence number solution are even greater than for that of the upper bound solution.